Alright, so we left off on, well, hopefully you had a good spring break. We left off on talking about z-scores. So I did say that if this quarantine continued and we're going to do this from home, that once spring break ended, I was going to start doing quizzes at the beginning of our videos. So the way you do this, just answer this quiz and just email it to me. But just make sure on the subject line, make sure you just write that this is the quiz, and I'll check it, and then I'll probably reply to the email saying that I got it or giving you some feedback on the answer. Other than that, I am posting your grades on Canvas. Under the assignments, you don't have to post, you don't have to upload anything. It's just the only way for me to put your grade on Canvas, I needed to create assignments. You can still continue emailing me your homework as PDF. That works perfectly fine. Don't worry about submitting anything. It's just a way so I could actually give you a grade through Canvas, and I'm trying to finish that this week. Sorry it's been taking me so long. I should have that by the end of this week. So, but if you have any questions, please email me. Or if you're following the Instagram, you can DM me. Whatever works best for you. All right, but here's the quiz. Since we ended talking about z-scores on the last video before we went on spring break, so here's the question. Two friends ran the LA Marathon. Chris's time had a z-score of negative 1.23, and Sarah's time had a z-score of negative 1.27. Who had the better time? So look back at that video, or if you wrote any notes down, think about who has the better time, and you have to think about what z-score means. So try to do that. Other than that, I mean, if you want, pause it here so you can reread the question. But I'm going to continue to where we left off in our PowerPoints. So we left off, I'm going to scoot this over a bit. I think we'll still be able to see. We left off on, so z-scores was the last example we did about interpreting z-scores. Now, the idea was being able to see where your data value is. So if I go back to the beginning here, so the idea was relative standing. So the idea is you want to know where your data value is, or what's the standing compared to all the other data values. And the first thing was we looked at z-scores. Now we're going to look at percentiles. And maybe you've heard of percentiles if you took the SAT, or if you're planning to take the GRE for grad school or whatever it may be. They use the percentile system. And what a percentile means, so what z-scores did, it told you where your data value was relative to the mean. So you could either be above the mean or below the mean, but it was based everything off that middle, the mean, where percentiles break the entire data set into 100 different pieces, because you think from like 1 to 100%. It's breaking up. Imagine if you did a number line and then you broke up little 1% like intervals for your entire data set. So here, the percentiles measures of location denoted, so that's a notation. There has a P and then a capital P with subscripts, which divide a set of data into 100 groups, and that's what I mean by 1% all the way to 100%, with about 1% of values in each group. So each percent sort of telling you where that data value is, and you can think about it like as a window or a range, and within that range, only 1% of your data values are in there, and you break it up into 100 different little pieces, and those little intervals are containing only 1% of your data values in each single one of those small intervals spread out throughout your entire data set. But it's more than just breaking it up into 100. It's very specific into what percentile you are in. So, but to be able to, I wonder if there's a better definition. So this is all I have here. So what a percentile does, it's telling you what percent of data values are below where that particular data value is. That's what a percentile means. So if you're like in the 27th percentile, that means 25% of data values are below that data value, whatever that may be. If you're in the 52nd percentile, that just means 52% of data values are below that one data value. That's what percentiles mean. If, let's say you take the SAT or the GRE, which I'll look at an example later, if you scored in the 90th percentile, that means 90% of, so depending how many people take the SAT, so imagine thousands took it, and if you scored in the 90%, in the 90th percentile, that means 90% of the people that took the test scored less than you. But you can also think about it vice versa. If 90% scored less, that implies 10% scored more or above what you got on your SAT score. So this is like a small, quick example of what percentiles are doing. So it gives you an idea of where you stand relative to all the data set. And that's sort of, I go back to this. Relative standing. So in your SAT score, it tells you where you stand relative to everyone that actually took the test. So if you're in the 80th percentile, 80% did, I guess for a better lack of words, did worse than you. But 20% did better. That's what the percentiles are telling you. So just keep that in mind. But how you can calculate a percentile, we use this formula here. And you don't need this part right here, this multiplying by 100. I think we talked about this the first couple weeks. Can't remember exactly, but I'm pretty sure we talked about how you can convert any decimal into a percent. And the way we do that is you move 2 decimals to the right. So for example, let me pull up. I'll go to the quiz just because I have this here. Let's say I'm trying to convert like 0.23. If I'm trying to convert this to a percent, I have to move that decimal place 2 places to the right. 1, 2, which leaves me with 23. And then you don't write the decimal, but technically that's what's happening. It's moving over 1. Hopefully you can see my little mouse here, but I'll do it with my finger. You're going 1, 2 to the right, and that now gives you 23. Let me look for the percent. 23%. We normally don't write this decimal here. It just implies that that's a whole number now. And that's what this is doing. Oh, wrong one, sorry. That's what this 100 is doing here. So this is the main formula that you need. You need to know the number of values less than X. X is the data value that we are focusing on. So that example about the SAT scores, your score would be X. If you wanted to know how you stand relative to everyone that took the test, your value, your score would be this X here, and then you want to know the number of values that scored less, and that'd be tough to do in terms of your SAT score, but that's essentially what they're doing on how they determine what percentile you're in. They get your score, they count how many scored less than you, but divided by how many actually took the test, so the total number of values. So they look at your data value, how many people did worse than you, for better lack of words, and then divide by the total number of people that actually took the SAT. So, and then all this multiplying by 100 does, it just converts this decimal here, because the numerator is always going to be smaller than denominator, unless, of course, the only time that it's not, the only way it can be is if you scored the highest. That means everybody else below you is going to be equal to how many people took the test, which you're going to get like 100th percentile, meaning that everyone did worse than you. There was not one person that did better. But again, that's just an idea about this. But normally your numerator is always going to be smaller than your denominator. And then that multiplying by 100, all that's doing is converting. Let me stop that. All that's doing is converting your decimal into a percent, which we can do that by just moving the decimal 2 places to the right. So that's what this is doing here. So here, let's do this example. So the airport Verizon cell phone data speeds listed below are arranged in increasing order. Fine. So this is data speeds, whatever measurement they're using. Again, the example I gave you were test scores. This could be a list of how many test scores of the SATs. It could be different heights. It could be many different things, because you can see where you stand relative to if you're doing the average height of PCC students and you collected all this data, you can actually see what percentile you're in terms of your height. But you'd have to see how many people are shorter than you, and then divided by the total number of people you asked their height. And then that would give you the percentile of where you are relative to everyone you asked. And you multiply it by 100, you move 2 decimal places to the right, and that gives you a percent. But here, this is our bunch of data speeds, and we're trying to find the percentile for the data speed of 11.8 Mbps. I think that's megabits per second. So if you look, it starts from the smallest and it increases as you're going through. And we're just trying to find the percentile of 11.8, which is right here. If we look at the previous formula, I need to know the number of values less than x. So x is the data value in question. The data value here in question is 11.8. So everything less than it are all these in the first 2 rows. So we know there's 2 rows, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 columns. So if you do 2 times 10, that means that's 20 of those 20 speeds slower than 11.8. That's the idea of less than x. In this case, it's speeds that are slower. So every situation, the context is different. If you're talking about height, that's shorter. If you're talking about speeds, it's slower. If we're talking about test scores, you can either think it's just lower or worse. That is just less than whatever data value you're looking at, and that changes from slower, lower, shorter, worse, and so on and so forth. So we know how many scored less. Now we want to divide by how many total values there are. So in our situation, if we look, including the 11.8, we already know there's 10 columns, but there's 1, 2, 3, 4, 5 rows. So here, if we turn on our calculator, it's going to be 20 divided by, and again, there was 50 data values we're looking at. And that gives us 0.4. So technically here, if you want, you can multiply. So whenever you just hit the multiplication, you sometimes get this A and S. And all that A and S represents is just your answer. So it's just taking the answer from the previous step and then including it here. If you wanted to rewrite 0.4, you could. But if you just hit multiplication, it's just telling you it's using the number from the previous answer and it's multiplying to it. You can multiply by 100, but like I said before, let's pull it up on, let's do it right here. So if we did 0.4, if I move this 2 decimal places to the right, I'm going to have a 4. That's moving it over once. But when I would move it over a second time, I have to include a 0 there because I'm moving it 2 times to the right. So I end up with 40%. The same thing is going to give me here if I multiply by 100. See, I end up with 40. And what this 40 is, it's actually a percent already. So, or not necessarily you don't have to say percent, or you can just say the 40th percentile. Oops. That's another way to word it. So that 40 means the 40th percentile. Now let's look and see if that's what we got. So here it says, for the solution for the sorted list of airport data speeds in the table, we see that there are 20 data speeds less than 11.8 Mbps, so the percentile value of 11.8 is equal to 40. So that means it's in the 40th percentile. If you're thinking about percentages, that's the idea of moving it 2 places to the right. You don't have to put 40%. You would just say it's in the 40th percentile. And just like I said before, what percentile means is that's the percent of values or data values that are below that particular variable in question. So in this situation, the way we would interpret it is a data speed of 11.8 megabits per second is in the 40th percentile. This can be interpreted loosely as this. A data speed of 11.8 megabits per second separates the lowest 40% of values from the highest 60% of values. We have, again, this is just notation. So P with the subscript of 40, that's the 40th percentile, is 11.8. So, again, there's different ways to interpret it. Like I said, the 40th percentile means that there's 40% of data values in this situation that have slower speeds than 11.8. So we're talking about data speed here. Something that implies less in speed is slower. So 40% of data speed values are slower, or there were data values that were slower than 11.8. But at the same time, if 40% were lower, you automatically know that 60% were higher. Again, percentiles always give the idea that that's the percent that are below the X. That's how they always interpret it. It's below whatever your X is. That's the percent that's below. But if you know what's below, you know what's above as well. It's sort of, they go hand in hand. So it's just something to keep in mind on how can you interpret what these percentiles mean. Like I was talking about the GRE. The GRE gives you, sometimes does not give you, I'm not 100% sure, but I think sometimes you're given a percentile. Maybe you don't get a score, or sometimes you get your score attached to a percentile. And what that score means, so on the right here, we have percentiles. And look, it says right here, percent of test takers scoring lower than the Scout score. So if you're in the 78th percentile, that means 78% of test takers were scoring below 161. And this is for the quantitative GRE scoring percentiles. So the general GRE, I think, has 2 portions to it. 2 of those portions, has 3 portions to it, and 2 of those portions, they give you sort of a percentile where you are. And they get, depending wherever you land, let's say if you're in the 59th percentile, 59% of test takers scored below 150. But at the same time, that also tells you that 41% scored higher than 155. So that's just something to keep in mind. Again, the interpretation part of what these mean. Same thing here. Percent of test takers scored lower than the scaled score. So whatever data value is in question, once you find the percentile, that percentile is telling you the percent of data values are below that variable in question. But at the same time, you automatically know the percent that's above it. Again, I say they go hand in hand with each other. But the issue with percentiles is that there's 100 of them. You literally have to break up all your data sets into 1% increments. That's there's only 1% of data values that exist at that data set. So that's very, very small. We want to be able to group our data sets a little bit bigger. So every percentile you are, so even though you're at the 40th percentile, means 40% are below and 60% are above. It also means 1% of your data values exist at that particular score or at that particular percentile. There's 1% of data values there. So the idea here, so in this 59, there's 1% of the test takers scored 155. And that's the idea of breaking it into increments of 1%. So 1% of test takers scored 155. Or you can say 59% scored below, 41% scored above. And there's just a different ways that you can interpret what these percentiles all mean. But instead of breaking your data set into 100 different little pieces, and all those little pieces represent 1%, we can break them up into larger groups. Because, like for example, when we looked at the empirical rule, we know within one standard deviation, 68% of our data values land within that one standard deviation above and below. That's a large amount of data values. With percentiles, at every percentile, only 1% of your data values exist within that 1%. That's so small. I'd rather group things a little better, same way like the empirical rule does. 2 standard deviations and I'm already sort of looking at all the 95% of the data values. So that's a lot, to be able to group them quickly and more efficiently. And there's a way to do that with percentiles. But there's a slight, it's still a tile, it's not percentile, but still this idea of breaking up percentages below and above. So just keep in mind with the notation. So n, total number of values in the data set. So remember, n is usually, you can think about it as your sample size, which your sample size is just telling you the number of data values that are in your data set. And don't forget k being used. For example, the 25th percentile, so you would say k is 25, or you can put p subscript 25, which that's the k here on the subscript represents that kth percentile, depending what the percentile is exactly. But to group them a little bit better, or a little bigger, there's quartiles. Like I said, there's still tiles, but these are quartiles. So think about a quarter. There's 4 quarters in $1. So that means, it doesn't mean we're going to have 4 quartiles. It means that we're breaking up our data set into 4 even groups, where each single group represents 25% of your data set. Remember, percentiles, each single group represented 1%, but it also represented what the percent of data values are below or what percent of data values are above. This breaks it up into 4 even pieces, and each single piece represents 25%. Because together, they represent 100%, which will include your entire data set and possibly your entire population. So quartiles break things up. There's not, and that's why there's 3 quartiles. There's not 4 of them. Because if you think about a sheet of paper, and if you rip a sheet of paper in 4 different pieces in 3 different locations, you end up with 4 different pieces. So 3 cuts gives you 4 pieces. If you do 4 cuts, you're going to end up with 5 pieces. So that's the reason why we only label 3 quartiles. For example, with this sheet of paper, I cut it 1 here. That's 1 cut. If I make 1 cut, now I have 2 pieces. If I make 2 cuts, I now have 3 pieces. But again, I don't want 3, I need 4. So then I make another cut. That was a horrible cut, but the idea is I cut this paper 3 times. Hence I have 1, 2, 3, 4 pieces. And that's the idea, that you have broken up, instead of breaking your entire data set into little 1% increments, you're breaking up your entire data set in 25% increments, where 25% of your data values are within that quartile, either above or below. So quartiles measure the location. The same way the z-score was telling you the location of your data value, but it based everything off the mean. Percentiles are also telling you where your data value is relative to everything else. And the quartiles are also trying to measure a location, which divide a set of data into 4 groups, with groups with about 25% values in each group. So these percentages are telling you, in percentiles, 40% scored below, 60% scored above. Quartiles, each single piece represents I made 3 cuts, but each single piece represented 25% of data values are within that 1 quartile. And maybe you're remembering where we saw these Q sub 1, Q sub 2, Q sub 3. And I'm going to remind you now. So remember, this is a stat class. I hit stat. And then on edit, you either hit 1 or enter. And that lets you go to your table. And then you can input data values here. Just find whatever value that you want. We can say 45. And then you hit enter. And then that populates that number into your data set. And then, if you guys remember that to find the mean standard deviation, the way we did that, we went again to stat, but instead of hitting enter on edit, we move 1 to the right where it says calc, to calculate. And on 1 vars, I hit enter. I think I don't remember where we put our data set, but remember, you want to make sure you put the correct column in here. So to do that, I'm going to hit second and then L sub 1. And then I leave the frequency lifts empty. And when I calculate, I have all the information we did before, which was finding the mean, finding the median, and a couple more things. So if we look at, I'm scrolling down on the computer. If we look at here, there's our Q sub 1. So let me bring this closer. There's our Q sub 1 and Q sub 3. If you're wondering where's Q sub 2, Q sub 2 is actually the median. It's the halfway point of your data sets. So at Q sub 2, or in other words, the median, 50% of their data values are below the median. 50% would be above the median, because, like I said, it breaks everything up into 4 even pieces, each piece representing 25% of data values. So like I said, we were going to look at these again. On the test, I had you guys label them just because the information was already here. I wasn't telling you what Q sub 1 and Q sub 2 were, but I know that you're able to find them because here, when there's one vars calculation, it gives us our Q sub 1, Q sub 3, and the median is our Q sub 2. And it breaks this up into this nice, like 4 even pieces. I should probably correct that. It's not each piece is going to be even, but the idea is each piece should represent 25% of your data values should be within those pieces. They're not always going to be exactly the same. And you're going to be able to see that when we actually graph these quartiles. So just like the way we did histograms and we talked about pie charts and bar graphs to sort of represent our data, and then we also talked about the distribution, if it was symmetric, if it was skewed left, skewed right, uniform. There's going to be a way that we can determine those same ideas using quartiles. But to be able to do that, we first need to find, again, what these represent. So again, the first quartile. So that's going to be the smallest quartile. What that does, in other words, that Q sub 1 is the same thing as your 25th percentile. Because your 25th percentile says 25% of your data values are below, where 25% are above. And that's exactly where Q sub 1 is. It's literally at the 25th percentile. Because to the left should be 25%, because there's nothing less than Q sub 1. So to the left of that represents 25%. Now to the right of it, but not passing the median, in other words, not passing Q sub 2, which is our second quartile, represents 25%. Just between Q sub 1 and Q sub 2, or in other words, Q sub 1 and the median. Yeah, Q sub 1 and the median. Now, if you're just looking at Q sub 2 or you're looking at the median, which remember, the median is another measure of center. It's directly should be, as long as there's no very large numbers, even though the median is stable. Is that the word I'm looking for? Sorry about that. I got tongue twisted. If we're just focusing on the second quartile, or in other words, the median, which is another measure of center, that means it's also the same as the 50th percentile, which 50% of data values are below, and that means 50% are above, because the median should be in the middle, because the median is not affected by very large or very small numbers, because remember, the median lists the data set from least to greatest. So if there's a very small data value, it's at the beginning, and with a very large data value, it's at the end. So it doesn't affect the very large, very small number do not affect the median whatsoever. Whereas the mean, it did, and we talked about that before. So that's what Q sub 2 is. In other words, it's the median. So it says right there, same as P sub 50, which is a 50th percentile, and the same as the median. It separates the bottom 50% of the sorted values from the top 50%. Where the first quartile separated the bottom 25% with the upper 75%. And then lastly, there's Q sub 3. So again, you're sort of cutting your data set. If your data set was listed on a number line, let's say if you had to plot all your data values on a number line. So again, with those 3 quartiles, it's breaking up your data set into 4 pieces. They're not always necessarily the same pieces, but you know percentages. Then the third quartile, 75% of data values are below that whatever variable is in question, but at the same time there's 25% above. So, which is the same thing as looking at the 75th percentile. The 75th percentile says 75% scored below, or sorry, 75% of data values are less than, or 25% of data values are greater than. So that's what they represent. Essentially what you're doing is to find, if you're finding the Q sub 1, Q